Here we are in section 1.6, and we're going to talk about some important ideas: dot product, norm, angle between two vectors, and distance. And a lot of these ideas, definitely the first couple, will stem from what we've all seen before, the Pythagorean theorem. Now, we're talking about these ideas not just in R2 or R3, but we're extending them to larger dimensions like R5 or R17. And though we can't exactly visualize what's happening in R17, we can extend the ideas of what we know in R2 and R3. And there are two big operations that we've already seen we've gotten a lot of good practice with. The first one was vector addition, which was something like if you have two vectors, the way that you add them is just, nope, not like that, by adding their individual corresponding parts. And then there was scalar multiplication, where we took a real number and just multiplied it by a vector, and you just multiply by each entry in the vector. So these are operations that we're totally comfortable with doing, and they have a lot of significance. They have to be met if we want a set to be closed, or to be a subspace. It has to be closed under these two operations. These are two really key operations. And now we're going to introduce a few more operations. You can take the dot product of two vectors. You can find the norm of a vector, and another word for this is the length of a vector. We're going to look at finding the angle between two vectors, and even the distance between vectors. But there is something that's fundamentally different about these operations as opposed to these guys. These new ones that we're talking about today, they will yield not another vector when you perform the operation, but they'll yield a real number. So this is a fundamental difference between these new operations that we're going to talk about today and the old famous two that we're familiar with. And as I mentioned, the real power is in being able to extend these ideas from ones that we can visualize, like R2. We know what it means to find a distance of a vector in R2 and R3, 2 dimensions or 3 dimensions. But now we want to extend how we do it there to an arbitrary nth dimensional vector space of real number vectors. And we'll start with a question that we definitely could have answered before this course. What is the length of the vector, let's say 3, 7? So we're in R2, let's see, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. So somewhere about right here, we've got this vector, and I want to know what the length is. And like the olden days, we can just use the Pythagorean theorem to find this. We're going to take, this squared plus this distance squared will equal this distance squared. And this distance squared is 3 squared. This is 7 squared. So we've got 3 squared plus 7 squared. And when we take the square root of that, that will give us the length of that vector. So let's see, that's the square root of, 9 plus 49 equals square root of 58. And that's it. This is the length of that vector. So this time let's ask, what is the length of the vector, let's say -2, 1, 3. We're still in a situation where we can visualize it. It just popped into 3 dimensions instead of 2, but we can still figure this out. So in 3 dimensions, I've got these 3 axes, and then -2, 1, 3. So that'll be like -2 on the x1 axis, 1 on the x2 axis will get us about right here. And then we want to go up 3 on the x3 axis. So this vector, we can still sort of visualize it, will look something like this, and we want to find the distance of this vector. Well, I mean the length of this vector. Well, the length of this vector, it's still using Pythagorean theorem. We'll just have to use it a couple times. So it's definitely this length here will be the square root of this squared plus this squared. And we know that this guy squared is, this is 3 squared. So the length will be the square root of this 3 squared plus, and now this guy we have to do a little figuring out here, what this length is. And when I look at it, I see that this actually, we could find it with the Pythagorean theorem as well. So that length there is the square root of 1 squared plus negative 2 squared. And so this is a number we could figure out too. So 9 plus square root of 5 will be some decimal number. And it looks like this ends up being about 3.352, which sounds reasonable. So that's the length of this three-dimensional vector here. Then the natural extension of these questions is to ask a question like, what is the length of the vector? Say that we want to find the length of the vector 5, 7, 2, 1, negative 3. This is sitting in R5, which is a 5-dimensional space. We can't really visualize it, so we can't sort of build up to an answer like we did here. And this is where we introduce the idea of a dot product. So we want to extend the geometrical ideas to the vector space Rn. Even if we can't exactly visualize these, they'll be helpful in a lot of ways in the future. And the two that will really be helpful to know are length of a vector and whether two vectors are perpendicular, and another word for perpendicular is orthogonal. So these two ideas we want to definitely have a good grounding on. So let's look at some practical examples. So the first thing we're going to talk about are dot product and norm. And norm is another word for length. And in this first example, I'm going to ask you to find something that I haven't even told you what it is yet. So find the dot product of these two vectors, 4, negative 3, and 2, 7. And I'm going to go ahead and find the dot product. And you're going to start to see what the process is for finding the dot product pretty quickly. So the dot product of these two vectors is going to be 4 times 2 plus negative 3 times 7. And so that's 8 minus 21, which is negative 13. That's the dot product of those two vectors. So even without giving you a definition of what dot product is, I bet you could figure out what the dot product of these two vectors are, these two vectors from R5. Think through what we did here, and could you extend that to these two vectors? So, probably already figured it out. The dot product of these two vectors are 4 times 1 plus 0 times 5 plus 1 times 6 plus negative 2 times negative 2 plus 3 times 1. And let's see, that's equal to 4 plus 0, which we won't write, plus 6, plus 4, plus 3. 4 plus 6 is 10, plus 7 is 17. So those two vectors give us a dot product of 17. So this operation, whatever it is, dot product, it takes two vectors and it yields a real number. And those two vectors can be in any dimension. So if you were trying to give the definition of dot product in some generic way so that somebody could find the dot product in any dimension, how would you write that? How would you write the dot product between two vectors? So first of all, we would definitely need to make them as arbitrary as possible, and so we would put them in n dimension space, and then we would write out maybe the two vectors themselves and then how to find the dot product. So this is good to think through, you know, now that you're becoming more sophisticated in mathematics and becoming more independent thinkers. How would I write the definition of the dot product? So like we said, you would probably take two arbitrary vectors, u, and u would have to be in n space to be super arbitrary. And we need to have two vectors to do this operation, so we need two arbitrary vectors. And you're going to list the elements in each of these vectors because you're going to need the names of each of those elements to define the dot product. And so u dot v, this is how we write the operation dot product. It looks like a multiplication, and it is a certain type of multiplication with vectors, but whenever you see this symbol, it means you're taking the dot product between these two vectors. It's not like a real number multiplication because of the context of what we're talking about. And so this will be, let's see, we multiplied the first two elements together, so u1 times v1, plus the second two elements together, u2, v2, and we kept on doing that until we got to the last element. And this was the dot product. So here it is, a really important quantity, the dot product of two vectors. And this is, we're sort of stair-stepping our way into finding the length of a vector. This is going to help us out with that. But it has other meanings also. One thing I want to note before we move on is I want us to think about what it would look like if you took a vector and did the dot product of a vector with itself. You know, what would that mean for this formula for the dot product? And think about in your own head what that would look like if we wrote that out. Hopefully you came to the idea that it should look something like this, because you're going to get u1 times u1, so that's u1 squared, u2 times u2, u2 squared, un times un, which is our un squared. So a vector dotted with itself, and boy, this starts to look a little bit like the Pythagorean theorem, or at least pieces of it, which leads to our next term, the norm of a vector. So the norm or length of a vector, we'll say u is, again, some arbitrary vector in n space. And even though we can't visualize n space, we do want to be able to talk about the length of a vector in n space. And so we're going to define it as the square root of this. So the way that we write the length or norm of a vector is these two double vertical lines, then whatever vector we're talking about. So the norm of the vector u is going to equal the square root of u1 squared plus u2 squared. This is all consistent with R2 and R3. What happens there with the Pythagorean theorem, plus un squared. And all of that is really just the vector, or the square root of the vector u dot u. So this is how we'll find the length of a vector, any vector in Rn. The norm or the length will be the square root of the vector dotted with itself, or dot producted with itself. So let's just do a couple examples where we're finding the length of a vector. Let's say that our vector u is 413. Then the norm of u will be the square root of 4 squared plus 1 squared plus 3 squared, which is the square root of 16, 17, 26. So this would be the length of that vector. And however many elements you have in your vector, you're just going to take the square root of each of them squared and then added together. So you could be in R17 or R63 space, and you could still find the length of a vector. So we got to go back to this example because I'm just realizing an error that we made, and that happens sometimes, in finding this length. This length definitely should have been the 3 squared plus this length here squared. And this was right, that it was the square root of 1 squared plus negative 2 squared, but we definitely needed to square this, which we didn't do. This is definitely So from here, this length will be 3 squared plus, okay, the square and the square root will knock each other out. 1 squared plus negative 2 squared. Okay, phew. This looks a little bit more like what the definition of norm should be. And that's the square root of 9 plus 1 plus 4, which is the square root of 14. And that sounds a little bit more reasonable, that we would get a little bit more length than just that 3.3. It won't be quite 4, but it'll be pretty close to 4. Okay, so that's great. It's, you know, oftentimes we learn it's valuable to kind of go back and see where we make mistakes, and we can learn things in a more really holistic way as we kind of poke at it from all sides. Okay, so we definitely needed to correct that. And now we're back on our examples of finding the norm, finding the length of a random vector in Rn, and we wanted it to, that previous example to look like how it should look, and so we fixed that. Let's look at an example in R5. Okay, so here we have this vector. I want you to take a minute, pause the video, and you find the norm for this vector. And you should have gotten the square root of 60 for the norm of that vector. One last one that I want to look at is this vector. We'll say u is 0, 0, 0, 1, 0. And what would the norm of that vector be? So again, I encourage you to pause the video and find the norm of this vector, and we'll check and see if we get the same answer. Hopefully you got 1 for your answer, and that was pretty obvious when we even were given the vector that that would probably be the case. None of these were going to contribute anything to the length, and so that 1, when you square it and then take the square root of it, is just going to be 1. Okay, before we move on to other ideas, there's a couple more things we need to talk about in regards to the norm of a vector. So there's a special name for a vector of length 1. So think, what would, if you were going to name a vector of length 1, what would you call it? And you would probably call it this, a unit vector. When you see that phrase, it means that the vector has length 1. And it can be in any direction. It doesn't have to be like the vector 1, 0 or 0, 1. It can be a vector in any direction, just having length 1. And the other thing we want to talk about is this phrase, to normalize a vector. What would that mean? If we want to normalize a vector, what that means is you're going to take a vector and you are going to you're going to construct a unit vector that's in the same direction of that original vector. So it's, you're either going to reduce the length of the vector or stretch it so that it has length 1, but it's in the same direction as the original vector. So we'll say to normalize a vector means to construct a unit vector in the same direction of your original vector u. And let's look at some examples of where we do this. So normalize the following vectors. And the first one that we'll normalize is just the vector 3, 4. So this vector 1, 2, 3, 1, 2, 3, 4 in R2 looks like this. And when we want to normalize it, we want to find what vector is in the same direction, but is only a unit in length. So what are the coordinates of this vector that has length 1, but it's in the same direction of 3, 4. So we want to find these coordinates. And so you think, what should our strategy be? Well, maybe a good starting point is to find out what the length of this vector is. If it's length 1, then we're done. It definitely isn't length 1, but whatever the length of this is, couldn't we divide each of these coordinates by that length and sort of, reduce the coordinates enough that they're in the same direction, same proportion between these coordinates, but it'll only have length 1. And so that's what we're going to do. So the first thing to do is find the length of this, and we use, we're going to find the norm of 3, 4. So that is So the length of the original vector is the square root of 3 squared plus 4 squared. And so that is the square root of 9 plus 16, which is the square root of 25, which is 5. Okay, this is the length of the vector. So 3 divided by 5 and 4 divided by 5. This will be the vector that's in the same direction as the original vector, but has only length 1. And you could go ahead and find the norm of this, and you'll see that it's going to be length 1. You'll end up with, 9 over 25 plus 16 over 25 is 25 over 25. Square root of that is 1. The length of this vector is definitely 1, and it is in the same direction as the original vector. Same story with this guy. It's a vector in R4. I can't draw a picture of it because I can't draw a picture of anything in R4, but I can still normalize this vector. And I'll start by finding the length of this vector. And the length of it will be the square root of negative 5 squared plus 1 squared plus 0 squared plus 3 squared. And that is the square root of 25 plus 1 plus 9, which is the square root of 35. Okay, and so a normalized vector in the same direction of this would be negative 5 divided by that length, and the next coordinate would be 1 divided by that length, and the next coordinate would be 0, and 3 divided by that length. It's fine with me if you leave it in, if you don't rationalize the denominator. The solutions that you see will probably rationalize the denominator, but I just want to see that you're dividing each element by the norm, and this will be, this will have normalized the original vector. Okay, so you probably remember back here when we talked about the two really big ideas would be length of a vector and whether two vectors are orthogonal. And we've pretty much, explored a lot about the length of a vector. You know how to normalize a vector, you know how to find the norm, you know how the dot product is important in that. Now we're going to shift our focus onto angles between vectors. So as we're introducing the idea of angles between vectors and keeping in mind that we could be talking about R17 or R23. So what would it mean for two vectors in that kind of space to have an angle between them? The law of cosines we extend to those vector spaces, and it leads to an important property . So say we have two arbitrary vectors in Rn, and we're going to call theta the angle between the two vectors. Then the cosine of theta is equal to the dot product of u and v over the norm of u times the norm of v. This result, and I'm just giving it to you as a result, the proof of this is on page 40 in your textbook. They go through it step by step. It's all derived from the law of cosines. But this gives us a way to calculate an angle between two vectors. And it really ties together some important ideas. This is the dot product between two vectors. So here's a question for you. Is this a dot product? Think about this denominator. Is this a dot product? No, it shouldn't be, because this is a real number just multiplied by a real number. But this one relationship here ties together three ideas. The idea between an angle between the two vectors, dot product of the two vectors, and the norms of the vectors. And we're also going to say that theta is between 0 and pi. So now I want us to think about sort of a big question. In this formula for the cosine of theta, that angle between the two vectors, what happens to that? So what if the dot product between those two vectors. You take the dot product and you get 0. Where would that lead us in this formula? Let's see. If the dot product of u and v are 0, that would mean that this whole fraction has to be 0. What does it mean for the cosine of an angle to be 0? So if u dot v equals 0, then that implies that the cosine of theta has to equal 0. And if cosine of an angle is 0, then what does that imply? Well, which angles have a cosine of 0? Let's see, if I remember the cosine curve, it looks something like this. And this is 1, this is -1, this is pi right here. So this is the cosine theta curve, y equals cosine theta. And this function, that cosine of theta is 0 at pi halves. And pi halves is like 90 degrees, and that is a right angle. So when cosine of theta equals 0, then we know that theta equals 90 degrees or pi halves. And that would mean that the angle between our two vectors was a right angle. These two vectors are orthogonal. So this is a big deal. When your dot product between two vectors are equal to 0, through a series of statements, we can figure out that the angle actually has to be a right angle. And so this right here implies that your two vectors are at right angles to each other, and that they're perpendicular, or another word for that is orthogonal. So we move from this big question to this big result. If u dot v equals 0, then u and v are orthogonal. And that just means that they are perpendicular. So perpendicular. And that's an important property that we'll spend a lot of time investigating throughout the course. So this result here, if the dot product between two vectors is 0, then those two vectors are orthogonal. So we're going to look at some specific examples and try to determine whether they're orthogonal or not just from this property. So the first two that we're going to look at are 5, 3, and what's my other vector here? Oops. How about -6, 10? Okay, so are these orthogonal? We can find out really quickly by just looking at the dot product of these two vectors. So that would be 5 times 3 plus, no, not 5 times 3. How about 5 times -6 plus 3 times 10? And it looks pretty suspicious. -30 plus 30 equals 0. Okay, so these, yes, these two vectors are orthogonal. You know what? Let's just sketch it real quick so that we can sort of prove to ourselves that that's true. So let's see, 5, 3 will be 1, 2, 3, 4, 5, 1, 2, 3. It'll be a point about right here. And then -6, 10 would be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's going to be a point kind of up there. And so that vector looks like this. And yeah, these definitely look orthogonal. They look perpendicular to each other. We can't tell exactly from a sketch like this if they truly are orthogonal, but the dot product verifies that they are. Okay, so you try this one and see if you can tell if they're orthogonal or not. So go ahead and pause the video. So when I did the dot product, I found out, yeah, they are orthogonal. And so I thought I'd just draw real quickly what they look like. 4, -1 is this vector here. And then 3, 12 would be really high up here. And yep, these guys look orthogonal too. Okay, one last example for you to try. So go ahead and pause the video and see if you can find out if 1, 5 and -4, 10 are orthogonal. I found out when I did the dot product, I got 46, and so I said, I probably shouldn't put an X there. So I said they're not orthogonal. And I want to just see what they look like when we graph it. So let's see, 1, 5 should be a vector right about here. And then, let's see, -4, 10, -1, 2, 3, 4 is this vector here. And yeah, even from my kind of rough sketch, I can tell that those are not orthogonal. They're not at right angles to each other. Okay, these were all good examples for R2. Let's look at an example in R5. So I have these two vectors in R5 and I want to figure out if they're orthogonal. So you go ahead and pause the video and decide if these two vectors are orthogonal or not. So when I took the dot product of these two vectors, I'm getting, I did all this, and then I'm getting 4 - 1 is 3. So it looks like I get 23 for their dot product. So these two vectors are not orthogonal. So the next example is an important one. We're asked to actually construct two vectors that are orthogonal to this vector in R5. We saw it back here, and we know that it's not orthogonal to this, but could we construct a vector or two vectors that are orthogonal to this? And so it's valuable to think through how would we go about doing this? How would we come up with a vector that is orthogonal to this guy? Well, we would know that whatever that vector was, when we took the dot product with this, we would have to get 0. So maybe there's a way just to kind of eyeball it and construct a vector whose dot product with this guy is 0. Maybe it's that easy. So that's probably the first thing we should try. So first of all, we know that we need to have 5 elements in our vector because it has to be in R5. And importantly, actually this middle vector here, it doesn't matter what it is because it's going to get multiplied by 0 and 0 out anyway. Remember that we want all of this to equal 0, this dot product. But we know that it doesn't matter what this middle element is, so we'll just say 17 because it's going to get multiplied by this 0. Now, we just need to be kind of clever about constructing the other ones. So what if for the first two elements, I say this is a 2 and a -1? Okay, so that would give me 2 times 1 is 2, and a -1 times 2 is -2. Those would 0 out. My third element is already 0, and I'm just going to force these guys to be 0 as well by making them 0. And this looks like a vector that when we take the dot product with this one will give us 0. Let's just double check. And the dot product will be 1 times 2 plus 2 times -1 plus 0 times 17 plus -1 times 0 plus 5 times 0. And that'll be 2 minus 2 plus a bunch of zeros, which is 0. Those are orthogonal. Okay, we just constructed it. Orthogonal. And pretty easily we could come up with another one. We could say, how about 2, -1, 15, 0, 0. that would also be orthogonal because that middle term always is a 0. So we've done what they've asked us to do. We've come up with two vectors that are orthogonal to that original vector. Okay, so we have talked about the idea of the norm of an angle, or the length or magnitude, it's sometimes called. We've also talked about the angle between two vectors, and importantly, whether or not they're orthogonal. Interestingly, both of these important topics we use the dot product to evaluate those. And now, lastly, we're going to talk about the distance between 2 points in Rn. We won't spend a lot of time on this, but we're going to touch on it. And we'll just extend the idea of distance between points in R2. So we literally are going to extend the distance formula from R2 into Rn, and this is what we get. If we have two vectors, x and y, each made of elements like x1, x2, all the way to xn, y1, y2, all the way to yn, then the distance between those 2 points, the two endpoints, is given by this formula, the square root of the difference of the first element squared plus the difference of the second element squared, all the way to the difference of the last element squared. And think about how you could write this using some things that we've already learned today. So this is also equal to, this looks like the norm of x minus y. I also want to mention that there is another name for dot product that you might come across, and that is Euclidean inner product. It's sometimes referred to as this, but more often it's called the dot product. Okay, last example for this section. This has been a really meaty section, a lot of material in here, and we're on our last example. So here is our job to do. Let W be the subspace of all vectors orthogonal to 1, 3, 1. So that is a subspace, I'll tell you that. So all the vectors that are orthogonal to that, so the set of all vectors orthogonal to that, and we're going to find three things. We're going to find a basis for this subspace, we're going to find the dimension, which won't be hard after we find the basis, and what does this look like? So first of all, finding a basis, and this is the more difficult of the tasks. How would we find a basis? Well, I'm just going to start by writing things that I know. Like, what do we know? If something is orthogonal to this, what do we know about it? What could we write down? Something about the dot product. If I have a vector in this subspace, then that vector, the dot product of that vector and 1, 3, 1, I know that that would have to equal 0 because they're orthogonal. Okay, so let's write this out as U1, U2, U3, dotted with 1, 3, 1 equals 0. Okay, well, I know how to do a dot product, so that would be U1 times 1, and that's U1, plus 3U2 plus U3 equals 0. Okay, so this is the only condition on the vector u, that this has to be true. Well, now this is starting to look kind of familiar to just some things that we learned before. What if I wanted to solve this for u1? Then u1 would equal negative 3u2 plus, nope, not plus, how about minus u3? Okay. Boy, what if I wanted to describe all the vectors that had this relationship? We've done this before. We just use parameters. So let R equal U2, let S equal U3, and we can describe these types of vectors using these parameters. So the solution to this equation, we don't really have a system of equations, but we have this relationship, this equation between, these three pieces of the vector. Then any vector that followed this rule would look something like this. It would have to look like negative 3r minus s, and then r and s. So these are all possible vectors u that are orthogonal, and I'll just draw this. This symbol sometimes means perpendicular or orthogonal, are all possible u. Let me write it like this, actually, such that the vector u is orthogonal to 1, 3, 1. Okay, so I'm on the right track. All of the vectors that look like this form a subspace, and I just need to write a basis for it. We've done this also before. So the basis of that set, let's see, I know I can write this set as R times negative 3, 1, 0. So this isn't really the basis yet. This is just the set, plus S times negative 1, 0, 1. Okay, and so this set of all these combinations, the basis for it will be negative 3, 1, 0, negative 1, 0, 1. I'm running out of room here. So this is a basis. This was the hard thing that we needed to find. And the dimension is 2. And if you took all of the, linear combinations of this basis, or in other words, this set of all possible vectors that are orthogonal to this guy, then you get a plane in R3. So now I'm going to do my best to try to help us see geometrically what's happening here and what this set might look like. So first of all, this vector here, 1, 3, 1. So that's 1, and then 3 on x2, and then up 1. So that vector will look something like 1. If you can picture it kind of poking out at us, pointing towards us, and elevated up 1. And then there's a whole host of other vectors that are actually orthogonal to this. There's one there, there's one here, there's one there. And this is all happening in three-dimensional space, but all of these vectors, and of course if this one's orthogonal, then an extension of that is orthogonal. So it's a whole plane of vectors that are orthogonal to our original vector, and it does form a subspace. So I hope I haven't given too much away with this example. I just kind of got excited. It's such a great problem that really envelops almost everything we've learned so far. Okay, that's a great section.